Welcome to our lecture on the FRTB SA algorithm, where we will review the calculation steps using a Python implementation migrated from last session's Excel reconciliation. Before we begin, please note the information regarding copyright and trademark. The outline is straightforward. We will set the stage of the lecture in an introduction. Then we will discuss the source code and how it aligns with the Basel regulation. Don't worry if you're not a programmer, as I believe any business analyst can read Python code when it's well structured. We'll summarize the lecture in the conclusion. Let us start. In this lecture, we will start with a concise recap of the FRTB requirements for general interest rate risk delta capital. We then streamline the standardized approach algorithm by translating the complex Excel logic into Python. The accompanying script calc FRTB SA charge for one swap was produced from last session's spreadsheet with a few manual tweaks in GPT 03 model. Next, we will walk through the code to expose every calculation, highlighting how the source itself can serve as your permanent reference. Being able to program an algorithm is clear evidence that you understand the mechanics. Because this Python version shadows each regulatory step, it offers an ideal step-by-step learning exercise. We will validate the script's output against the original spreadsheet's results. All of this applies directly to the single swap example examined in our previous lecture. The Basel text from January 2019 outlines the calculation of the delta capital charge. For general interest rate risk with a single risk factor, this is done by applying risk weights to delta sensitivities and then aggregating these using prescribed cross-tenor correlations. The aggregation formula expresses the total variance as a quadratic form, where weighted sensitivities are combined using a correlation matrix. Key components include risk weights, which are given and defined for each tenor bucket. Cross-tenor correlation measures how exposures at different maturities relate to each other. It is calculated as the maximum between an exponential decay function and a minimum correlation threshold. This expresses the main conceptual rationale of the charge. We are now going to go through the source code and the logic of the program. If you like, you might want to pause and look at the program that is attached to the lecture. It's about 100 lines of code. The structure of the lecture is that we have 4 blocks and we explain for each block what it does and then look at the source code. The Python code takes 3 main types of inputs. First, it defines 8 USD SOFR delta sensitivities. Second, it defines the BIS risk weights. Third, it uses parameters such as lambda and the row floor. These inputs form the basis for further calculations in the process. This code block defines several hard-coded inputs for trading system risk calculation. The first section, labeled as trading system delta sensitivities in USD, lists tuples of tenor values and their corresponding delta sensitivities. For example, at a tenor of 0.25 years, the sensitivity is negative $1,095,000. At 3 years, it's over $16 million. The second section provides Basel risk weight parameters from January 2019 table. They are shared in a dictionary where each key is a tenor and each value is the associated risk weight. For instance, both 0.25 and 0.5 year tenors have a risk weight of 2.4%. The variable square root t stores the square root of 2 and will be used for low correlation scenario adjustments. Finally, there are cross-tenor correlation hyperparameters. Lambda represents the decay factor for correlation set at 0.03, while floor sets the minimum correlation floor at 40%. These parameters control how correlations between different tenors decrease with distance, but do not fall below the specified floor value. Now, let's look at the second block of code. First, the code generates weighted sensitivities using the build data frame function. This step scales each sensitivity by its corresponding risk weight and multiplies by 1 divided by the square root of 2. The scaling standardizes the inputs for later aggregation. Next, correlations are applied using the correlation matrix function. This function constructs a basal cross-tenor correlation matrix called sigma. In this matrix, all diagonal elements are set to 1. The off-diagonal elements decay exponentially as tenors become more distant from each other, but do not fall below a specified minimum value or floor. This approach reflects how correlations between different tenors decrease with distance, but remain above a certain threshold. This slide presents the two Python functions just described. The first function, build data frame, creates a Panda data frame containing weighted sensitivities. It starts by generating a data frame from the input data with columns for tenor and scale values. It then maps each tenor to its corresponding risk weight, adjusting by dividing with the square root of 2. The function then multiplies the scaled value by its risk weight to compute the weighted sensitivity for each row. The second function, correlation matrix, constructs a cross-tenor correlation matrix. It initializes an identity matrix where diagonal elements are 1. For each pair of tenors that are not equal, it calculates their correlation using the exponential decay based on the difference and minimum value. This approach ensures correlations decrease as tenors become more distant from each other, but do not fall below a specified floor value. These functions help quantify instructor risk exposures across different maturities or tenors in financial portfolios. Let's move to the third code block out of 4. The Python code calculates the GIRR FRTB charge using the function GIRR delta charge. This function computes sigma, which is the charge, as a square root of W transpose times sigma times W. This sigma is the end result, and in the Excel it was in sheet consolidated view in cell C4. This calculation provides a measure of risk based on weighted sensitivities and their correlations. Now, we have again the source code of the function, here GIR delta charge, takes as input the Panda data frame, which is the weighted sensitivities. It first computes the correlation matrix using the tenors from the input data frame. Then it extracts the vector of risk weights. The portfolio variance is calculated by multiplying the risk weights with the correlation matrix and then again with the risk weights. Finally, it returns the square root of the absolute value of this variance as the capital charge. This approach follows standard quantitative finance practices for calculating portfolio level capital requirements under regulatory frameworks like FRTB. In a later slide, we will actually relate this portfolio variance calculation to modern portfolio theory. The last block is very straightforward. The main function accepts a parameter that controls whether detailed interim results are shown. The function then executes two core functions in sequence. Finally, it returns the calculated FRTB charge. Let's look at this in the code. The main function accepts an optional argument list. It uses argparse to handle command line arguments, allowing users to specify options such as exporting data to a CSV file. The script builds a data frame using build data frame and computes the GRR delta charge with GRR delta charge function. The consolidated charge is printed in US dollars with 6 decimal places. If the user provides a CSV path, the data frame is saved as a CSV file at that location and confirmation is printed. Finally, if the script is run directly rather than imported as a module, it calls main to execute these steps. The structure ensures modularity and flexibility for both direct execution and reuse in other contexts. This table compares the results from the Python script and an Excel spreadsheet for this specific charge. The input parameters are the same for the two approaches, Excel and Python. The Python script produces a value of 4,950,860 US dollars, which is about $74,264 higher than the Excel amount. I believe this difference is approximately, or it is 1.5%, and it's probably likely caused by rounding difference in the spreadsheet calculations. If both methods use precise settings for rounding, this discrepancy would probably be eliminated. Let's do a quick detour into the theory of the calculation method Basel applies and that we just presented. We connect FRTB's general interest rate risk delta charge to classical portfolio theory. Start with the Markowitz variance equation, sigma p squared equals the weighted vector transposed times the covariance matrix times the weight vector. In our setting, the weights Wi are the weighted delta sensitivities, which I labeled as I. The covariance matrix, capital sigma, becomes the cross-tenor correlation matrix, rho ij. The resulting portfolio variance, sigma p squared, maps directly to the GRR delta variance, written as S transpose rho S. Taking the square root of that expression gives portfolio risk, sigma p, which is exactly the capital charge, the square root of the absolute value of S transpose rho S. So please take away these 3 points from the slide. The same quadratic engine drives value at risk, conditional var, and the FRTB standardized approach. Basel provides the volatility via risk weight tables. We, the practitioners, construct the correlation matrix rho. In code, this is a one-liner. V equals S dot transpose at rho at S times. K equals the square root of the absolute value of V. Let us conclude, as we covered Excel, Python, large language models, and a little bit of portfolio theory. Large language models offer a valuable use case in this context. The LLMs can take complex Excel files and convert them into clean, well-documented Python code. This is applicable to this lecture for educational purposes, but also in practice. Python provides greater clarity and transparency, especially when dealing with Excel files that have many interdependencies. Example-based code helps illustrate how the functionality works by providing clear and concise explanations. Reviewing the attached Python code and running it yourself will provide a strong learning experience, and I highly recommend it. So, we began with a quick introduction, then walked in detail through the Python code line by line. We briefly showed that the GRR delta variance is just the Markowitz quadratic form variance in disguise. And finally, we wrapped up with the key takeaways and next steps. I hope you enjoyed this lecture, as I certainly had fun pulling it together. Thank you for attending the lecture. And if you have any questions or comments, please do not hesitate to reach out via the comments or email. I'm looking forward to seeing you in the next session. Thank you.